Remember, the final exam is going to come in two parts. The first half of the exam is going to cover units 1 and 2, and the second part of the final exam is going to cover just unit 3. So just this new stuff. Okay, I've separated it out because this newer stuff is newer to you, so that also gives you a little more time. And remember, the second part is going to be Wednesday and Thursday of finals week, and you'll be able to choose any 2-hour block during those 2 days to work on the test, okay? I cannot give any extensions beyond Thursday, 11:59 p.m. The class ends Thursday at 11:59 p.m. of finals week. Make sure you have everything done before then. I can give an extension to the first part of the test if you need it, but not the second part. So let's talk about lesson 22. Lesson 22, like I said, is exactly like lesson 21, except lesson 21 is if there's 2 samples or 2 different things we're comparing, and lesson 22 is 3 or more things we're comparing. Okay, so example 1 here is a fully worked out example. What I ask you to do is just to read through it and just walk through it, and I'll show you what's happening here. Okay, so at a community college, the math department experiment with 4 different methods of teaching algebra. At the end of the semester, the students were given the same final exam. A selection of exams was chosen at random, and the results are shown here. So this is percent on the final exam based on each type of learning method. We want to know if all the methods are equally effective or if any of the methods resulted in a different means on the exam. What we're trying to see is, just like the on-time flights for Delta versus American, the null hypothesis was that the averages are the same, the proportions are the same, and our alternative hypothesis is literally going to be that at least one of them is different from the other. That is going to be used for every single one. We're not trying to say one's more, one's less. 3 of them might be the same and 1 of them might be different. Okay, we don't know how they're different. And with 4 options, there's a whole bunch of ways that could play out. These 3 could be the same and this one could be less. These 2 could be the same and these 2 could be the same. But there's a whole bunch of different ways that could play out. So all we're trying to say is that our null is that they're the same, and our alternate is that at least one is different. That's what I was saying, where in these later lessons, it's nice because this is the same for every single thing you do. Just copy and paste, copy and paste. What we need to do is we need to put this data into our calculator, and then we'll run this test, and it's called the ANOVA. Okay, so we got a p-value of 0.42. So that same thing happening here. If the P is low, that ho's got to go. Is the P low enough? No, 42% is way bigger than 5%, so the P ain't low. And yes, it looks like I wrote paint. So the calculator is doing all of the work for us. All we do is we're putting in raw data into the lists, and we're running this test, and we're getting a p-value out. It's still a hypothesis test. Okay, so let's look at an example. I'm going to pop down to example 3. A firm wishes to compare 4 programs for training workers to perform a certain manual task. 20 new employees were randomly assigned to a training program with 5 in each program. At the end of the training period, a test was conducted to see how quickly they can perform each task. The number of times the task is performed per minute is recorded for each trainee with the results below. Using a 5% significant level, so alpha equals 0.05, determine whether the treatments differ in their effectiveness. Okay, so we're just trying to find out if they differ in their effectiveness. So we're going to put this into L1, L2, L3, and L4. Actually, let's work on the null and alternate hypothesis first. The null hypothesis is that all programs are the same, and the alternate hypothesis is at least one of them is different. It's as easy as that. Literally, for every single one of these, that's how we're going to do it. Now we're going to put this in our calculator. Stat, arrow over to tests, and I'm going to use the up arrow, and you see ANOVA is the very last thing on here. Press enter. All the other tests we've been doing, we've been putting in information. This relies on us having data in our lists. So what we need to do before we can run this ANOVA test is we need to put data in our lists. So go back to stat, and remember edit is talking about editing the list. So we're going to press enter, and you see I have information here, so I need to clear it. Remember, arrow up, press clear, press enter, go over here, arrow up, clear, enter, over here, arrow up, clear, enter. I'm going to go back. L1, I'm going to put in program 1. Now I should have the same number of values in each one of these. So I've got an extra one in L3, 12, 14, 11. Oh, I put 11 twice. Clear won't get rid of it. I need delete. There, okay. Arrow down to this extra 11, and I'm going to press delete. There, and see how it got rid of that extra 11? Okay, now arrow over to L4, 9, 8, 7. Now we can go back and do our ANOVA. So we're going to press stat, over to tests, arrow up, ANOVA, press enter. Oh, okay, you see how I have ANOVA? That's bad. I have to press clear, otherwise I'll get an error, and now I got to start over. Stat, over to test, arrow up to ANOVA. There we go. Now in ANOVA, you strictly just tell it what lists are my data in, and it crunches a whole bunch of numbers, and it's going to spit out a p-value for us. So our lists are in L1, L2, L3, L4. So second one gives you the L1, okay, and then I have to put the comma, and the comma is right here above the 7. L1, comma, second 2 gives us L2, comma, second 3, comma, second 4. I just had 4 pieces of data. Now close the parentheses. Okay, anyone need help getting this bit? Now press enter. And there is your result. This F, this is like a z-score. Okay, we're not using this. This is what they refer to as the test statistic, which we're not using. Okay, here's our p-value, 0.003. Okay, and it tells us a whole bunch of other stuff. Don't worry too much about this. Again, this is an introductory class. We're just sticking with the p-value. P-value is 0.003. So 0.3%. Is that P low? Is that hoe going to go? Okay, 80% of you are correct. So yes, we do reject the hoe because the P value is lower than the alpha, the level of significance. Okay, we wanted alpha equals 0.05, which is 5%, and our P value is 0.003, which as a percent is 0.3%, so less than 1%. Okay, so we do reject that hoe. P-value is less than the level of significance, so we reject the null hypothesis. So we do have sufficient evidence that the mean number of tasks performed is different across the training programs. And I'm sorry, I know the formatting on this one is weird. I'm not sure what happened. So there is a difference across these training programs. Monday, we're going to cover lesson 23, which is chi-square, which is again more stuff on the hypothesis testing. There's 2 different things happening in lesson 23. So in a lot of ways, lesson 23 is kind of 2 separate lessons taught together because they are related to each other. The first part, it's a hypothesis test to see if things are shaking out the way we think they should be. Okay, so for example, anyone here like M&Ms? Do you think the proportion of M&Ms in the bag is the same for every single color? All right, so most of you say no, it's not. And it turns out it's not. M&M recently released the proportions of colors for each M&Ms. And for example, let's talk about blue. Blue M&Ms make up 24% of the M&Ms. Okay, but there's 5 colors. I forget the exact proportion, but they're not evenly distributed. If we knew what exact proportions those were, when you get a bag of M&Ms, if you were to figure out how many of each color were in that one bag of M&Ms, would you expect it to be that exact proportion every single time? Yeah, no, you wouldn't, right? Because you know enough now about sampling, and you know that samples all vary. No matter what you know about the population, it's not likely that what you see in the sample is going to be exactly what you expect to get from the population. That's what the entire class has been based on, right? The first part of the lesson 23, we're comparing what we expect to see, what should be happening in the population versus what we actually see in our sample. What we see in our sample is called the observed value, and what we see in the expectation is, what the law says it should be, or what M&M's Mars says it should be. There's what should happen theoretically and what we're actually seeing. What we're doing is called a goodness of fit test. And that goodness of fit test means, is this proportion that we're seeing, yes, our sample is different, but is it close enough to what we expect to see that we can call it okay? If it is close enough, then we call it a good fit. And if it's not close enough, we call it a bad fit. Okay, and that's where the whole goodness of fit comes in. Are our proportions close enough to call it okay? Okay, even though it's not exactly what we see in the sample. And then the second part is what we're doing is we're determining if two things are independent. And you remember from lesson 11, we learned about independence of things. But now what we're going to be doing is we can just put it in our calculator, and our calculator will determine if those things are independent. If working from home is independent of whether or not you have children. Do people who have kids, are they more likely to work from home? Is being a Democrat make you more likely to smoke pot? Those kinds of independent, dependent questions. And I say that because that was actually one of the examples that I had last year, but I don't know where that example went. That's always a fun example to discuss. It turns out that yes, Democrats are more likely to smoke pot. That's your fun fact for the day. Thank you for your time. It was lovely to see you all.